Another common way to describe the rate of a reaction is by using half-lives. We use the half-life, we use the term T or time to the 1/2. Is a reaction is the time it takes for 1/2 of the reactant to be used up. So the concentration of the reactant continues to decrease by a factor of 2 with each half-life. Here's a graph that shows how half-lives work. Initially, we have a beaker with a concentration of 0.8 molar. After one half-life, or 1 minute, for instance, is the half-life, we have half of that initial concentration. So after one half-life, we have 0.4 molar. After 2 half-lives, we have half of that value. So after 2 half-lives, we have half of 0.4, which will then be 0.2. After 3 half-lives, we will have half of that second half-life value, so 0.1 molar. It's tempting just to take the initial concentration and divide it by 3, but it's not the case for this. You have to individually divide it by 2 for every single half-life. We can also rearrange the integrated rate law to solve for half-lives specifically. And this is just the derivation of that. Don't worry about knowing that. I just want you to know this. If you have a first order reaction, you can use the half-life equation to solve for K, or if you know K, you can solve for the half-life. So the half-life equation for a first order reaction is the natural log of 2 divided by K. So for that first order reaction, the half-life is constant and is independent of the initial concentration of the reactant. What we mean by that is if you look in this equation, nowhere in that equation is the initial concentration of the reactant. So that means that it is not going to affect your half-life, just your rate constant. So for first order reactions, the half-life is inversely proportional to K. That is, the slower the reaction, the longer the half-life. And for first order reactions, the rate constant can be determined by measuring the reaction's half-life. So we can either solve for K or solve for the half-life with this equation. Example 14.7 says a first order reaction has a half-life of 63.4 minutes. At 225 degrees Celsius. Calculate the rate constant for the reaction. So we're looking for K and they gave us the half-life. So if I multiply K on both sides, I will then get K times the half-life is equal to the natural log of 2. I can then divide by the half-life on both sides, and I isolate K, and that's just going to be equal to the natural log of 2 divided by the half-life. So now I can plug everything in. My K is equal to the natural log of 2 divided by my half-life, so 63.4 minutes, which is 0.0109 minutes to the minus 1. Now, they didn't actually specify they wanted that rate constant in seconds, so I'm just going to leave it in minutes and save myself some time. But it's important to always know what the units are, because if they were asking for seconds, we would then need to calculate 63.4 minutes into seconds. So we would just divide it by 60, or we would multiply it by 60. Let's move on to second order reactions. In 14.2, we know that the rate law for a second order reaction looks like this. So that 2 is always going to be the second order. We can also use calculus to obtain the integrated rate law because we want the second order reaction to give a linear graph when we plot it. So the way we can do that is if we find that 1 over your concentration is equal to KT plus 1 over your initial concentration. So your y-axis will be 1 divided by your concentration, and your x-axis will be time. So y is equal to mx plus b. So k is going to be your slope, and your y-intercept is going to be 1 divided by your initial concentration.